Welcome to today's lesson. I'd like to begin by having you work on this warm-up dealing with function composition and then check. Okay, the answers that you should have gotten here, you can see that you would plug in the g function into the f function. You'll plug it in both locations here and then simplify and get your answer for that. As far as any domain restrictions, both of these are polynomials, so we would not have domain restrictions on those. Okay, today's lesson is going to be section 2.8, one-to-one functions and their inverses. Okay, for looking at these, if you look in this first diagram here, this is representing a one-to-one function because each domain value in A is paired with one range value in B. If we look at this this scenario here, G is not what we call one-to-one because you've got two input values that are being paired with the same output value. If we were to write these as ordered pairs, we would have 4, 10, 3, 4, 2, 4, and 1, 2. So this would be a function because the x's are not repeating, but it's not going to be what we call a one-to-one function because the y's are repeating. So when the y's repeat, it's not a one-to-one function. And that's an important characteristic for it to be one-to-one. In order to have an inverse, it needs to be one-to-one. So the first part of this section, we're going to be talking about determining if functions are one-to-one. Okay, notation here, the inverse function, we use this little negative, the -1 to represent the inverse. That is not the -1 power. So if you recall, we would have x to the -1 would be equivalent to 1 over x. That's when that's an exponent. This is not an exponent, it's simply notation that represents the inverse. So it's not implying any kind of like power that you're going to work with. It's just for notation to indicate it's an inverse. Okay, a function with domain A is called a one-to-one function if no two elements of A have the same image. And that's what we saw with that diagram that we just looked at. Basically, what we're saying here is that if the two function values are different, then the original inputs also had to be different. Okay. So one way we can check for determining if something is one-to-one is by assuming that the two function values are equal and then actually showing that the x's had to be equal as well. So a condition for being able to say it's one-to-one is that f of x sub 1 is if f of x sub 1 is equal to f of x sub 2, then x sub 1 had to be equal to x sub 2. Okay, so we are going to look at something called the horizontal line test. The horizontal line test is basically the test that's going to test to see if a function is one-to-one. It works just like the vertical line test. If I draw a horizontal line and it touches in two places, then that means it has two output values that are assigned, or it has one output value that's assigned to two input values, and therefore it would not be one-to-one because of that. So if it fails the horizontal line test, meaning it touches in more than one place, then it's not one-to-one. Okay, so just to kind of summarize, the vertical line test will determine if it's a function, and the horizontal line test is going to determine if it's one-to-one and therefore has an inverse. Okay, so if we look at this graph here of x to the third, this is the cubic function, and any horizontal line that we can draw is going to only touch it one time. Even though here at the origin it looks a little bit flat, it is, if we were to zoom in, you would see that it continues to rise, and therefore it would be one-to-one. Okay, here you're asked to determine, is this one-to-one? So I'm going to give you a minute to put this in your graphing calculator and apply the horizontal line test and see what you think about whether it's one-to-one. Okay, this is the graph you would get. So if I were to draw a horizontal line, obviously it's going to touch it twice. So it's going to fail the horizontal line test and it's not going to be one-to-one. one thing that if you notice, if a function is either always increasing or always decreasing, it's going to be 1 to 1. So if I had a function and it was always decreasing, something like this, then that is going to pass the horizontal line test, and it's also going to be 1 to 1. So always increasing, always decreasing would be 1 to 1. Now, if I have a function that does something like this, that's not always increasing because we have this little part here that's decreasing, and it would clearly fail the horizontal line test because it would touch multiple times there. Okay, on this graph here, if we were to look at this one, if you graph this, you would be able to clearly see that it's not 1 to 1 because both g of negative 1 is equal to 1 and g of 1 is equal to 1. Okay, here's one that I want us to look at and show algebraically that it's 1 to 1. So for this, we're going to assume that f of x sub 1 is equal to f of x sub 2, and we're going to try to show that that means that x sub 1 has to equal x sub 2. So I'm going to evaluate my function at x sub 1, so I'm going to have 3x sub 1 plus 4 equals 3x sub 2 plus 4. I'm just doing function evaluation of this function here. So if I subtract 4 from both sides, I'm going to get 3x sub 1 equals 3x sub 2. We'll divide by 3 and get x sub 1 equals x sub 2, and that's what we needed to show in order to show it's 1 to 1. So I have a function here for you to, and I'd like for you to do this algebraically, not by the graph, to determine whether the function is 1 to 1. Okay, so we start by assuming that g of x sub 1 equals g of x sub 2. So we plug that in, we get the square root of x sub 1 equals the square root of x sub 2. We'll square both sides, and that gives us x sub 1 equal to x sub 2, and that's what we were needing to show. Okay, when we start talking about inverses of functions, we need to keep track of domains and ranges. So basically what happens is if we have a function, a one-to-one function with domain A and range B, then when we look at its inverse, the domain of the inverse is B and the range is A. So we get our A's and our B's to switch. Because if you think about it, this is your X and this is your Y. But when you do the inverse, your Y is going to become your input value and your X is going to become your output value. So you switch your input and your input and your output, which means you switch your domain and your range. Okay, so the domain of the inverse is the range of the original. The range of the inverse is the domain of the original. One thing to kind of keep in mind is that the inverse basically undoes or reverses whatever the original function did. So whatever f does to something, f inverse undoes. So here, if you've got these different values given, these are x's and these are y's in each case. And we want to find f inverse of 5. So with the inverse, this is the y. So what we want to do is we want to look and find where y is 5. So y is 5 here. So that means my input value to do that, cause it to be 5 was 1. So my answer for this one would be 1. F inverse of 7, again, this is my y, so I'm going to go to where y is 7. So my input value that gave me 7 as an output would have been 3. Here, I need to find where y is negative 10, so that's going to be this one. So the input value for that would have been 8. Okay, so here's a couple to practice with. So if we're wanting to find the value for f inverse of 19, then that's just going to be 5 because F inverse undoes whatever F did. So F sends us this way, F inverse sends us back. Okay, so if F inverse is 86, this is the Y and this is the X. So now I need to find, if this is the X, then I need to find the Y. So that's going to be 86. Okay, here we have an equation. And again, this is going to act like the Y. When you're doing F inverse, your input value is the Y. So that's going to be, I'm going to put this negative 28 in the place of what's equivalent to the Y. So I'm going to have negative 28 equals 2 minus 6x. Because remember, y and f of x are basically equivalent to each other. Okay, so if I subtract 2, I'm going to get negative 30 equals negative 6x. Divide by negative 6, and so x is going to be 5. Okay, we can do function inverses of functions using a graph as well. So keep in mind, again, if I'm doing f inverse of 1, this is my y, and I've got to find the x. Okay. So I'm going to go to where y is 1. So here's my y-axis. I'm going to go to where y is 1, and I'm going to go across and down. So normally I start on the X and I go up and over. Here I'm going to start on the Y and go over and down. So that value then looks like it's going to be 6. If I look at F inverse of 4, then this is my X. So I'm going to go to where X is, sorry, this is my Y. I'm going to go to where Y is 4. So I'm going to go over and I'm going to go down. I'm going to get a value of 2 for my answer. We can also do these using tables. So if I'm going to do F inverse of 0, again, this is the Y. So I'm going to go to where the Y is 0, and then I'm going to give the X for my answer. So this one will be 4. Here, this is a composition of some inverses. So let's just take this first one first. So F inverse of 0, I'm going to go to where Y is 0, and that's going to be 4. So all this would be replaced by 4. And then I'm going to do F inverse of 4. So I'm going to go to where the Y is 4, and I'm going to give the X, and so that answer should be 6. Okay, we have what's called the inverse function property. So it says if let F be a one-to-one function with domain A and range B, then the inverse function satisfies the following cancellation properties. And that is that if we compose F inverse of f of x, then we get x. Because remember, they undo each other. So because they undo each other, we end up with what we started with, which was x. So in either order, whether it's f inverse of f or f of f inverse, if you compose the two together and they are inverses of each other, then that's going to simplify to give us x. Okay, so if we look at this one, we want to show that they're inverses of each other using this inverse property here. So I'm going to look at f of g of x. Because if they're inverses of each other, then we need to show that f of f inverse of x is actually going to equal x. So if I put g into f, I'm going to get x to the 1/3 to the 3rd. These cancel because I multiply my exponents and I get x to the 1st, which we know is just x, and that's what I need to show. If I wanted to go in the opposite direction, because it really doesn't matter which direction I go, I don't have to do both, I just have to do one. I would have x to the 3rd, and I'm going to put that into the 1/3 power into this function here, so I'm going to have x. If we look at this one again to show that they're inverses of each other, we need to compose f and g together, and we need for it to equal x. So I'm going to put g into f, and I could go the other direction as well. Okay, the 3's cancel, and I'll have x minus 4 plus 4, and that equals x. So they would be inverses of each other. Okay, finding an inverse. This is a little bit more complicated, but not difficult. So I have the steps outlined here for you. If we have the function 3x plus 6, this is a line, so it would pass the horizontal line test, so we do have an inverse. So to find out what that inverse is, we have to go through this process. And the first thing says we're going to replace f of x with y. So we're going to get rid of this function notation and just have a y here. We're going to interchange x and y, and that goes back to the, interchanging your domains and ranges when you talk about inverses. So we're going to switch the x and the y. So I had a y here, now I have an x. This x becomes a y. And then we're going to solve for the new y. This is where the problems may vary a little bit because depending on what you're working with, it may be more or less complicated. So this one, if we're solving it for y, we're going to move the 6 over, and then we're going to divide by 3. And this is actually another line, so if we were to break this up, we would have 1 over 3x minus 2. That's going to be my inverse function. We do like to carry it all the way back to replacing the y with the inverse notation, and so that's going to be the inverse of the function. If I wanted to, I could compose this function and this function together, and I should get that it equals x, therefore verifying that they are in fact inverses of each other. Okay, here's another one. It's a little bit more complicated. We want to start out by replacing the f of x with the y, and then interchanging the x and the y's. And then from here, this is where it gets more complicated because what we want to do is we want to actually cross multiply. So I'm going to multiply x times y minus 1. So I'm going to go this way, and then I'm going to multiply across this way. Okay, simplify. And then we want to move, and this is the part that I see people make the biggest mistake with. You want to get everything that has a y in it on one side and everything that doesn't have a y in it on the other side. So that's a very important step. Get the y terms together and the non-y terms together. From here, factor the y out as a GCF. And then now that allows us to be able to divide both sides by the x minus 1 so that we can cancel this. And then that leaves us with our inverse. So this is the inverse of what we started with. So it turns out it's its own inverse. Okay, so here's one for us to practice with. If you feel comfortable, try it. If not, then listen as we go through here. So we want to start out by replacing this with y, and then we're going to interchange our x and our y. And then finally, we're going to solve for y. And then that is my inverse. Okay, here's another one. Again, try it if you feel comfortable. If you don't, then keep watching. So we'll start out replacing this with y. Interchange the x's and the y's. And then now we're ready to solve for y. This is one where we're going to cross multiply. So that's going to give me 2 times x will be 2x. Cross multiply here, we'll have y to the 5th minus 3. Okay, we're going to add 3 to both sides. And then we're going to take a fifth root of both sides, and we get this for our inverse. So f inverse is going to be the fifth root of 2x plus 3. So just like a square root cancels a square, a cube root cancels a cube, a fifth root's going to cancel this 5 here and leave us with the y. Okay, here are a couple others for you to practice with. So go ahead and try both of these, and then we'll take a look at what you should have gotten. Okay, on this one, we were asked to find the inverse of the function 2x plus 3 over x minus 1. Okay, so first thing we want to replace this. Switch your x's and your y's. Okay, we want to cross multiply. So we'll multiply across here. So 1 times 2y plus 3. And then x times y minus 1. Okay, we'll simplify. Then we're going to group our y terms together and our non-y terms together. And that's a really, really, really important step. So anything that has a y on it comes together on one side. So I'm going to move this over. Anything that doesn't have a y in it goes to the other side. Okay, now we need to factor out our greatest common factor here, which is a y. We're going to divide by the 2 minus x. So I'm going to get f inverse of x equals negative 3 minus x over 2 minus x. So that's going to be my inverse function here. Okay, on this one, what you should have done first is to replace the f of x with the y. Then we're going to switch the x and the y. We're going to cross multiply. So I'll have x times y plus 4 equals y. Distribute. And then we're going to get our y terms on one side, which means we're going to bring this y over. And anything that doesn't have a y is going to go on the other side. Okay, from here, we're going to take out a y. Don't forget to leave your placeholder here. So this would be an x minus 1. And then divide by x minus 1 to get the y by itself. So our inverse function is going to be negative 4x over x minus 1. Okay, when we graph the inverse of a function, because we actually interchange our domains and ranges with this, what happens is the inverse is actually a reflection in the line y equals x. So this is our line y equals x, the diagonal line that passes through the origin and has a slope of 1. So if I have the point AB on my graph, then the point BA is also on the graph. And so because of that, we end up with this reflection along the line y equals x. So if this is my original function, then I reflect it in the line y equals x, and the red would be my inverse function. Okay, so on this one, if we want to sketch the graph of this function, the square root of x minus 2, and then use that to sketch the graph of its inverse, and then find an equation for the inverse. So looking at this, we're going to start out here. This is our square root function. So if we look at the diagonal line and reflect it over that, this point is going to get reflected here. The point 3, 1 is going to be 1, 3, and so forth. So we get this line of this equation, this function here on the graph that's a reflection in this line, y equals x. So to find the equation for this, what we're going to need to do is we're going to replace the f of x with the y. Then we're going to switch our x and y. And then we need to solve for the new y. So in doing that, once we switch these, we need to square both sides. So we'll have x squared equals y minus 2, and we'll solve for the y, and so y is going to be x squared plus 2. So one thing I want you to notice is that that this is only half of a parabola, kind of on its side. But then when we come down here and we solve for our inverse, it's actually the entire parabola that looks like this over here. Okay, and that's not the best drawing of it, but so we have to kind of restrict our domain. So if we look at this original function, this was our f of x, and we restrict its domain, we can see that the domain for this is from 2 to infinity, and the range is from 0 to infinity. So what happens is when I'm going to use this inverse function over here, I can't use the domain of it, which would be all real numbers. I actually have to restrict it. So I'm going to switch these. I'm going to interchange these. So the domain is going to become the range, and the range is going to become the domain. So in using this, I'm only going to look at the part from 0 to infinity, and that's the part that we see graphed here. So that's why this part is not actually part of it. It's just the part of the graph from 0 to infinity that matches as the reflection of this original graph here. So it's because of the domain restrictions and switching your domain and your range that we end up with that restriction there. Okay, so that takes us to the end of this section. Please contact me if you have any questions, and hope to see you in the live sessions with Zoom. Have a good day.